Okay, so before we start today, does anybody have any questions for me? Yep.
So I'm doing an assignment, just wondering like how simplified you want the formula.
How simplified do I want the formula on the assignments? So it's fine to have formulas that, like, you know, if your formula has 1,000 factorial in it, I don't need to see the decimal expansion of 1,000 factorial. It'll take up 2 pages.
What if, like, for example, like 9 to the power of like n minus n to the power of n minus 3? Is that okay?
Yeah, so if you have, I mean, if your formulas have symbols in them, then there's not too much you can do. Like, you know, if 10 to the n shows up in your formula, you can't write it, you can't really make it any simpler than that. So I'm not too fussy about that. What I would not like to see, for example, is if your formula has a sum in it, when actually that sum is easily evaluated to a symbol formula, that kind of thing. Because for the things that don't nicely simplify, we typically have notations for them, right? Like n factorial is really, it's just a shorthand because you end up often with this annoying n times n minus 1.
Also, the formula I just described, like, I just realized that technically I could take the -2 out of it on the second part.
Yeah.
But like, is that?
So, I mean, simplify as much as possible while maintaining its correctness.
Okay.
Other questions? Okay, so today we're going to talk about mainly about binomial coefficients, which most of you have seen before. I think you guys call them combinations for most of the way you've learned them in high school. But before we get there, there's just a distinction that I want to make that's really important that sometimes gets lost, and that's the difference between a set and a sequence. So most of you remember the salient properties of a set are that it's a collection of distinct elements. So for example, A, B, and C are 3 different things. And there's this little word in there, it's an unordered collection. So for example, if I write the set like this, A, B, C, in these curly braces to indicate that it's a set, or I write the set like this, curly braces B, C, A, those are actually the same set. I mean, they use slightly different notation for those 2 things, but those 2 things are equal. They're the same object. What is different from sets are sequences, where a sequence basically is exactly that, a sequence, so one after the other of things, and the order that these things appear matters. So for example, the sequence ABC, that is not the same as the sequence BCA. And because we're counting things in this course, for example, well, there's some obvious things, but you know, what is the number of sets on ABC? So sets of size 3 on ABC, well, there's one of them. Doesn't matter how you write it out, it's the same set. On the other hand, what's the number of sequences that consist of 1A, 1B, and 1C? Well, that's a different story. There's more than one of those, because look, there's at least 2 here. All right? So when I say sequence, it really means order matters, and order means the order that they appear in the sequence. So I don't mean somehow sorted order. For example, you might say, oh, this one is in sorted order, but this one is not. No, order really means just the order that they're written down in the sequence. Okay. So first, knock this off. Permutations. So remember, we have this definition. N factorial is equal to 1 if n is equal to 0. Otherwise, it's equal to 1 times 2 times 3, and so on, all the way up to n, which is the same thing as n times n minus 1, and so on, all the way down to 1. And that's if n is bigger than or equal to 1. Okay. So here's a theorem. The number of permutations of an n element set is n factorial. So for example, if I take a set S, which is A, B, C, so permutations, I think most of you have seen this word before. So permutation of a set is a sequence in which every element of the set occurs exactly once. So for example, the permutations of ABC are ABC. They are ACB, BAC, BCA, and CAB, CBA. So there are 6 of them, and 6, so 6 should be 3 factorial because these are all the permutations of a 3-element set, and indeed 3 factorial is 3 times 2 times 1, which is equal to 6. All right. That's what I want to say about permutations. How do you prove this? Can someone tell me how you would prove this? Yep.
Well, wouldn't it be using the product rule? Because the first one you have n different options, then n minus 1 different options.
Yeah. So the proof is just the product rule with an n-step procedure where the ith step chooses the ith element in the permutation from the n minus I minus 1 elements not already chosen. So for example, if I want to write a permutation of this 3-element set, the procedure works as follows. In step 1, I choose one of these 3 elements, write it down. So maybe I choose B, and now I'm not allowed to choose it anymore. So I have 3 choices for this step. In step 2, I choose one of the 2 remaining elements. Maybe I choose C. There were 2 choices for that step, and now I'm not allowed to choose C anymore. And then finally, in the 3rd step, I choose the last remaining element, which is A. There was only 1 choice for that. And so the total number of ways I could have done this is 3 times 2 times 1. Okay. Is there another proof of this? So,
represent again?
what's that?
I represents what? Oh, I represents how many there is in total.
I represents the step, which element you're choosing. So this is step 1, step 2, step 3. So I equals 1, I equals 2, I equals 3. Here we had 3 minus 0 choices. Here we had 3 minus 2 choices. Here we had 3 minus 1 choices and 3 minus 2 choices. Okay. There's another proof of this, but and it uses something we already know, which is the following. If I write down a permutation like this, then I can write the indices beside it. Looks like this. Okay. So actually, right, so B is at position 1, C is at position 2, and A is at position 3. So that means if this is a permutation of a set S, another way to look at it is actually it's a function from S up here onto the integers 1, 2, 3, up to the size of S. So in this case we set an n element set, so up to n. And is there anything special about that function? Yep. It's a bijection, and in fact, even more simply, it's 1 to 1, right? Everything in S appears in exactly one place here. So each thing here has exactly one thing in S at that position. So this is a 1-to-1 function. And it's a 1-to-1 function from a set S of size n onto another set of size n. And we saw a theorem that actually counted the number of 1-to-1 functions from a set of size n onto a set of size m. So even more general than that. But if you plug in that formula, you'll see that it's n factorial. Okay. So there's a bijection between permutations and 1-to-1 functions from sets of size n onto sets of size n. Okay. So here's the next thing. And I want to be really clear that we don't confuse the definition with some results later. So here's a definition. N choose K denotes the number of K element subsets of a set of size n. Okay, so let's take an example. We'll take a set S with 4 elements, so n equals 4. And let's look at all of its K equals 2 element subsets. So those are A, B, A, C, A, D, B, C, B, D, and finally C, D. 1, 2, 3, 4, 5, 6. Okay. So if I did this carefully enough, I will have listed every pair of elements in here shows up in exactly one of these subsets. So if I did this right, that means that for choose 2, the number of 2-element subsets of a 4-element set is equal to 6. And we'll very soon see a formula for this thing, but let's not confuse the formula for the definition. I mean, we'll prove that this is equal to some formula, but the definition is just this. It's the number of k-element subsets of a set of size n. And this is, these things are called the binomial coefficients. For a reason that we'll also see very shortly. Okay? Two element subsets. So n is equal to 4, k is equal to 2. So let's look at a couple of examples. I have a deck of 52 distinct cards, so a standard playing deck, and a hand is a set of 5 cards. How many different hands are there? So lots of variants of poker. Deal like this. You're dealt 5 cards out of these 52. The order that you hold them in your hand doesn't matter, right? It doesn't matter the order in which you receive them. They're just really a set of 5 cards. So the answer is, well, how many 5-element subsets are there of this 52-element set? And so just really by definition, the answer is 52 choose 5, which is happens to be that. We'll see how we get that number soon. So, 2.5 million different hands. So it's hard as a human player to know what the best thing you should do is for every given hand. It's a bit much to remember. Here's a less obvious one. How many n-bit binary strings have exactly k ones? So for example, here is a 6 positions for a binary string, so n equals 6. And let's say I ask how many of those have exactly, how many binary strings can I write of length 6 that have exactly 2 1s in them? So here's an example of such a thing. Binary string of length 6 with exactly 2 1s. Here's another example. And there's some more. So the question is, how many are there? So how would you create a 6-bit binary string that has exactly 2 1s?
Pick 2 out of 6.
Pick 2 locations out of those 6 positions to put the 1s. So maybe I pick this one, and then I have to put zeros everywhere else. Okay. So sounds like there's a procedure there for writing these things, and the procedure is choose k locations for the 1s, write 1s at those k locations, write zeros everywhere else. Choose k locations for the 1s. What does that mean? Well, I mean, the locations are, you can think of them as numbered 1, 2, 3, 4, 5, up to n. So that just means this is a k element subset of 1 to n, right? Here, the subset is 1 through, the set is 1 through 6, and I choose 2 elements from 1 through 6, 2 and 5, and that's where the 1s go. So there's a 3-step procedure. How many ways are there to do this first step? So about half of you are saying this is a stupid question because it's too easy. There's another fraction of you which are completely lost. And I won't continue until someone tries to answer. Yep. Not quite, because it doesn't matter if I choose 2 and then 5, or if I choose 5 and then 2, because I'm going to write 1s in both places anyway. Yep.
Well, you could treat the 2 1s as one object, so then you have 4 other columns to deal with. So then you have 5. But then that's like 5 vectors.
No, but I don't need the exact number. Just do we have the number of ways to choose k locations for the 1s, which means I choose from 1 through n, I choose k things. Is there a name for that? The number of ways to do that? It's written on the board over there. It's n choose k. I'm choosing a k element subset from a set of size n. The number of ways of doing that, the definition is n choose k. Okay. So this procedure has the number of ways to execute step 1 is n choose k. The number of ways to execute step 2, well, there's only one way to do that. The locations are already chosen. All I do is write down the 1s there, so that's fixed. And then I have to write down all the zeros in the remaining locations. There's only one way to do that. And so the number of ways of executing this is n choose k times 1 times 1, so n choose k.
Why is it 2 1 and why is it 3 1?
Because once I've chosen the k locations that I'm going to write the 1s in, this just says write the ones in those locations.
Oh, okay.
There's no choice there. And again, here, there's no choice. Write the zeros in the other locations.
Oh, okay, so there's 3 steps, and choose K locations, and write ones of those Ks. Oh, okay.
Yeah. So the only thing to choose is where the ones will go, and that's just a subset of K things from this n element set. If you like, actually, we compared binary strings. When we did the bijection rule, we looked at n-bit binary strings, and we looked at subsets of a set. And the bijection that we used was, if the set is called x1 through xn, then I'll just make the ith bit equal to 1 if xi is in the subset, and 0 if it's not in the subset. And then you'll actually notice that that means subsets consist of size k correspond exactly to binary strings with exactly k1s in them. So there's actually another way to do this just by bijection between subsets of size k of an n-element set and these n-bit binary strings with k things in them. But that's all that's happening here. Okay. So now we've just been using this n choose k as some kind of a symbol. Let's actually figure out what the value is, the formula for this is. So here's the theorem. N choose k is equal to n factorial over n minus k factorial k factorial. Okay. Now, we're going to prove this theorem. So some of you may, this is where I said I want to distinguish between the definition and this result. So some of you may have learned that n choose k is defined to be this thing. But it's more useful to define it as this number of k-element subsets and then prove that that's equal to this thing. And the proof of this is going to use a technique that the book calls a combinatorial proof, but it's in most places called double counting or counting in 2 different ways. And it's one of my favorite proof techniques. And it basically involves defining a set and using the rules that we know, something like the product rule or complement rule or something, to figure out the size of the set. So we're going to do something like, we'll define some set A, and we'll compute the size of A. And we'll get some answer, blah. Okay? And we do that using the product rule or whatever our toolbox says. Then we forget about this proof that we just did to show that the size of A is equal to blah. And we go back and we try and calculate the size of A different way. Maybe first time we use the product rule, and next time we use the complement rule. Or maybe the first time we use the product rule with one procedure, the next time we use the product rule with a different procedure. And we go ahead and we do this, and we figure out that the size of A, using this other calculation, is foo. Okay, and we're surprised because we got 2 different answers. We go back and we check all of our steps that we used to figure out that the size of A is equal to blah, and we check them very carefully, and they're all correct. And we go back and we check that all the calculations and things we did to determine that the size of A is equal to foo, and that's also correct. And so what do we conclude then? Yep.
The size of A is foo, and the bijection rule is bijection rule.
No, but someone shouted it out over there. foo is equal to blah. That's the only thing that can happen here, right? Foo is equal to size of A is equal to blah. Equality is transitive, so foo must be equal to blah. And we'll see over and over in this course, we use this trick, and we do this, and just by applying the rules naturally, we get some formula over here. We apply the rules naturally some other way, we get some formula over here. On the surface, those two formulas don't look anything alike, but we did everything correctly, so they must be equal. And we'll do that a bunch of times today, but let's do it now. And the set A that we will introduce, A is equal to the set of all k element sequences that use each element of S at most once. Okay, so I have a set S like this. So here n equals 4. And let's take k equals 2. And I would like to know how many k element sequences are there that I can make where I use each letter at most once. So for example, AB is one of those things. BD is one of those things. CA is one of those things. AC is one of those things, different than CA, and so on. Okay. So I think there's an easy way to tackle this. If we want to prove that prove something about the size of A using the product rule, what's the natural thing to do? So I want to write out two characters from S, two different characters. What's the first step? Choose the first character, right? So I want to write a two-character sequence from S. I need to make a choice for the first character. Maybe I choose B. How many options did I have? Well, at that time, I had 4 options. Now I need to choose the second character. How many options do I have? 3 options. Maybe I choose D. And now I'm done. So there were 12 of these, 4 times 3, 12 of these two-character sequences I can make like this. And more generally, if the size of A is n, and I'm trying to make a k element sequence, then I need to choose the first thing in the sequence. How many options are there for the first thing? From an n element set, there's n. Now when I choose the second thing, how many options are there? n minus 1. And for the third thing, there's n minus 2. And someone said n factorial, but it's not quite n factorial because we only want a sequence of length k. So this goes on for a while. Finally, we choose the kth element in the sequence. And the restriction we have at that point is that we're not allowed to choose any of the k minus 1 elements that we already chose.
So it goes up to K?
it goes from n down to n minus k minus 1.
And you said it's a k-length.
Yeah, so I'm looking for k element sequences that use each element at most ones. Okay? And this, we've seen a trick. This is a thing that starts out like a factorial but gets truncated. And so we saw that we can complete this because if we put here n minus k factorial here and n minus k factorial here, then on top we get n factorial, and on the bottom we get n minus k factorial. Okay. So we've determined that the size of A is equal to n factorial over n minus k factorial. Let's forget about that, and let's think about another way we could have made one of these k element sequences. A different procedure, a different way to count them. This one is slightly less intuitive to me, but also makes sense. So the other way to do this is to say, step one is choose k elements from S. So for example, here I might choose B and D. Okay, so I know my sequence is going to have B and D in it. And then step two is choose a permutation. For those k elements. So in step one, I chose B and D. In step two, I decide, actually, I'm going to write this as D followed by B. All right. So how many subsets of size 2 could I have chosen from this 4-element set? 4, choose 2. How many subsets of size k could I have chosen from this n-element set? I could have chosen any of the n choose k ones. Again, that's just the definition of n choose k, is number of k-element subsets of an n-element set. Now I have to choose a permutation for those k elements. How many permutations are there of a k set of size k? It's k factorial, right? So there's k factorial ways to do that. And then if I do that, I get an element in A. I get an ordered k element, a sequence consisting of k elements from A, no element repeated. So that must mean that the size of A is equal to n choose k times k factorial. All right. So that must mean that n choose k times k factorial is equal to n factorial over n minus k factorial. Now that's not quite what we want to prove. Let's go back and look at what we want to prove. We want to prove that n choose k is equal to this thing. But wait, this is really the same formula, right? Divide both sides of this by k factorial. The k factorial disappears over here and shows up over here. And that's what we were trying to prove. And how did we do that? We did that by defining some intermediate set A that let us, when computed its size 2 different ways, and then realizing that, well, both of those things must be equal. Yeah?
Number 2, elements, why did we use k factorial?
Well, the first theorem we did today was that the number of permutations of an n-element set is n factorial, so the number of permutations of a k-element set is k factorial. Yeah?
Can you just go through or product from step 1 to 2 where you get to just that transition?
Yeah. Yeah, so we're applying the product rule here. And this is our procedure. This is our procedure for generating, what did I call them? K-element sequence that uses each element of S at most once, right? I choose K elements, then I pick an order to write them down in. This many ways to do the first step, this many ways to do the second step. Okay. So, questions so far? All right. So let's remember those things. So now we know the difference between a set and a sequence. We don't need this anymore. N choose k. We figured out that that's equal to n factorial over k factorial n minus k factorial. And we're going to look at where this name binomial coefficients comes from. So let's go back to, I don't know, grade 9, grade 7, grade 8, depends where you come from. So x plus y squared. That's a nice concise way to write that. What's the long way to write that? Yeah?
X plus y times x plus y.
Sure. X plus y times x plus y. Is there another way to write that? Yeah?
X squared plus xy plus y.
Yeah. And let me do that a little bit more slowly. So this is the answer, but let's see how we got that. Anybody remember there's like a mnemonic for this?
FOIL.
FOIL. First, inside, outside, last. So what does that mean? Well, that means when you take the product like this, you have to make sure you get every pair of terms where one comes from this part and the other one comes from the second part, so the first part and the second part. So first refers to the first thing in each part, that's the x squared. And notice there were 4 terms there, first, outside, inside, last. There's 4 letters there. But there are only 3 terms in the answer, so something happens in between. So first, outside. Outside is x times y. Inside is y times x. And last is y squared. And that's what you end up with. Okay? And the one I want you to notice is this xy showing up twice. And why did that happen? That happened because of the 4 ways I had of choosing these things, 2 of them gave me an x and a y. One of them was x from the first, y from the second. The other one was y from the first, x from the second. So somehow this 2 has something to do with the number of ways of choosing something in a specific way. Anyone know this offhand? Yeah.
X cubed plus 3xy plus 1 over time. Sorry. X plus y right.
That one. Okay. And how did I get that? Well, if I wanted to do it the long way, I write out x plus y times x plus y times x plus y, and I have to try all of the 8 different terms that I get by picking something from here, times something from here, times something from here. And there's 2 ways to pick this, 2 ways to pick this, 2 ways to pick this, so there's 8 different ways. So if I do this the long way, I'm going to get 8 different terms, but this term shows up 3 times, and this term shows up 3 times. And when does 3x squared y show up? Well, it shows up when I pick x in 2 of these places and y in the other one. Right, so for example, I could say x, x, y, x, y, x, y, x, x. There's 3 ways to get that. All right. And then you can ask what happens with x plus y to the 4th. And that's when you get what the book calls Newton's binomial theorem, but I'm not actually sure that that's Newton's binomial theorem because Newton proved something more general that worked for certain non-integer things. But the theorem is the following. For any integer n, x plus y to the n is equal to the sum k equals 0 to n of n choose k, x to the n minus k, y to the k. All right, let's check that, for example, see what that tells us about x plus y cubed. So this is a sum that starts with k equals 0. So in this case, n is equal to 3. And so we apply this formula. So it says that the first thing is when k equals 0. So we get 3 choose 0 times x to the 3 minus 0, so that's x to the 3, y to the 0. The next term is 3 choose 1, x to the 3 minus 1 is 2, y to the 1. The next term is 3 choose 2, x to the 3 minus 2 is x to the 1, y choose y to the 2, and then the final term is when k is equal to 3, 3 choose 3, x to the 0, y to the 3, and if we clean that up, 3 choose 0. So the number of 0 element sets of a 3 element set, that's 1. There's only the empty set is the only 0 element set. So that's just 1 times x cubed, y to the 0. This 3 choose 1. I have a set of size 3. I want to choose one element from it. How many ways are there to do that? Well, there's 3 ways to do it. Three choose 2. How many ways are there to choose 2 elements from a set of size 3?
3.
Why 3? So you can use the formula, or one way to choose 2 elements from a set of size 3 is to decide who not to choose.
Yeah.
So you leave one out, choose the one you're going to leave out, the other 2 go in. So, in fact, we'll see that more formally. So 3 choose 2 is 3, and then this is xy squared. And then finally, how many ways are there to choose 3 elements from a set of size 3? There's only one way to do it. I have to choose them all. Okay. And that's Newton's binomial theorem. And the proof, actually, we've kind of seen it already. I mean, we've seen it on this example. Here's why. Just make this bigger. Right, this x plus y to the n is really this thing, right? You write x plus y out n times. And the strategy that we use here and here works. You know, you have to pick, you're going to have 2 to the n terms. Each term you get by picking x or y here, picking x or y here, picking x or y here, and so on. And if I choose y k times, that means that I chose x n minus k times. Okay. So if I look at x to the n minus k, y to the k, how many times does that show up when I do this super long and boring process? Well, it happens every time I chose y exactly k times, and the x's have to then be chosen n minus k times. Well, how many ways are there to choose y exactly k times? Well, just how do you do that? Well, you choose among these n spots, choose the k places where you're going to pick y. There's n choose k ways to do that. So that's how often this thing will show up in that extremely long sum. So it's going to show up n choose k times, and that's what this thing tells you, right? The coefficient of x to the n minus k, y to the k, is just n choose k. Okay? So you can use Newton's binomial theorem to impress your friends at parties. You know, I'll just show you one example. And it's nice because it just lets you pick out for this big you know, the answer to the x plus y to the n is a big thing. It has n plus 1 terms, and lets you pick off the coefficient. So, you know, at a party, someone might say, what is the coefficient? I'm not saying that it's a fun party. Of x to the 12, y to the 13, in 2x minus 5y to the 25. Answer that correctly and you get a free beer, let's say. And if you haven't already had too many free beers, you'll realize, I can use Newton's binomial theorem for this. But then if you've had maybe one too many free beers, you'll say, oh no, but Newton's binomial theorem was about x plus y to the n, and here I've got 2x minus 5y to the n.
The plus negative.
So it doesn't apply. No, it applies because 2x plus 5y to the n, that's 2x plus minus 5y to the n, right?
So what's how you do it?
This thing plus this thing to the n. And that's the right format. Something plus something to the n. So we can use it. And what does it say? Well, we're interested in x to the 12, y to the 13. So the y to the 13 tells us that we're going to have a 25, which is n. Choose 13. Attached to that, we're going to have 2x to the 12 and minus 5y to the 13, right? This is the first thing in the formula. This is the second thing in the formula. That's what shows up. And what does all that work out to? 15, 2 to the 12. We're going to have x to the 12, y to the 13. What happens to this minus 5 to the 13? What is that?
Still minus 5 to the power 13.
Minus 5 to the power 13. Is that a positive or a negative number?
Negative.
It's a negative number. So you want to write this cleanly. The number will be negative, and over here you'll have a 5 to the 13. So, and that is your ticket to the free beer. Don't forget the negative sign. Okay. So now I would like to talk a bit about these combinatorial proofs. And do a few of those. So here's a lemma, and I already explained how you get it. For any k, I don't know, let's say any integer n bigger than 0 and any k between 0 and n choose k is equal to n choose n minus k. So, can anybody explain to me intuitively why this is? So we'll do something really silly. We'll say let A be the k element subsets of an n element set S. So A is all the k element subsets of an n, so the set of k element subsets of an n element set S. So what's the size of A? It's not a trick question. I'll give you a hint. In this particular lecture, if you just shout n choose k, like to almost every question, it's probably the right answer.
N choose K.
N choose k, right? The definition of n choose k is it's the number of k-element subsets of an n-element set. A is all the subsets, k-element subsets of an n-element set, so definitely that's the size of A. But there's another way to compute the size of A. So I want a k-element subset of an n-element set S, but I'd like a sort of alternative way to define it. We saw this example with k equals 2 and n equals 3. So here's a procedure. Choose n minus k elements from S. Then take the k elements you didn't choose. What's the result of this procedure? It's a k-element subset of S, right? So it's just as easy, I mean, whether I choose the elements k-elements that I want, or whether I choose the n minus k elements that I don't want, at the end I still get a k-element subset. But when I look at it this way, well, that gives me a different answer when I count the number of ways to do this procedure, because here I'm choosing n minus k elements from S, not just k. So the number of ways to do this is n choose n minus k. The number of ways to do this is only one. Once I've chosen this set, we're done. So that says that the size of A is n choose n minus k. What were we trying to prove? Oh, we're trying to prove n choose k is equal to n choose n minus k. So yeah, we've accomplished that. Forget about A in here.
Which one represents taking the k elements you didn't choose? Like, it says choose n minus k elements from S, I know it's n, and then in the bottom n minus k. Is n over k the k elements you didn't choose?
This n minus k is the set of elements that I don't want in my set. And choosing the elements I don't want gives me the same result as choosing the elements that I do want. It's just in one case I choose n minus k of them, the other case I choose k of them, so there must be this, the number of ways to do those two things must be the same. So it's sort of surprising-ish thing. Of course, from this formula you can also get it because look at what happens when you reverse the roles of k and n minus k here. But you get it combinatorially.
The elements you don't want is the same as the elements you want?
Yes. Yeah. Okay, so here's another one that I have a picture of over there. It's called Pascal's identity. And it says that n plus 1 choose k is equal to n choose k plus, yeah, that's right. N choose k plus n minus plus n choose k minus 1. Make sure I didn't make a mistake, which will show up immediately. Okay. So that's interesting. So here's what we'll do. Let S be an n plus 1 element set with a special element that we'll call X. Let A be the number of K element, or let, not the number of, be the set of K element subsets of S. Okay. Can somebody tell me the size of A?
Plus 1?
Good. You didn't say n choose K. S is a n plus 1 element set. A is all the K element subsets of S. So by definition, this is the number of ways to choose K elements from the set S. So I'm trying to use this combinatorial proof or double counting proof, which means now I need another way to compute the size of A. Well, in a way that gives me an answer that looks like this. And there's a hint on the board that says there's a special element, X. What does my set S look like? It has n plus 1 things in it, and one of those things is X. Then there's a whole bunch of other ones. In fact, the number of those other ones is n. Yep.
Will proofs be on exams?
The exams will be multiple choice, so there'll be questions about proofs on the exams. And to answer some of the questions, you'll have to basically do a proof, convince yourself that you have the correct answer. So if I look at how to get a K element subset from S, there's sort of two ways to do it, right? Two ways to get one of these things. Maybe I put X in my subset. Yeah? So let's say a X is the subsets in A that include X, and since they include X, and they also include K minus 1 other elements. And let A not X be the subsets in A that don't include X. So, if I have a subset of A, of K elements from A, well, it either includes X or it doesn't. So, let's say I'm interested first in the ones that don't include X. How many of those are there? So that means all the K elements I chose from these n elements. So how many are there? and choose k. So the size of A not x, the ones that don't include x, is n choose k. It's just me choosing k elements, not being allowed to pick x.
So all the dots inside the circle, like inside the inner circle, is
The inner circle is just to show you that this is n things. And there's the n plus 1 one right there.
anything that doesn't include the x.
Yeah. Okay. And how many ways are there, how many subsets are there that do include x?
K minus 1.
So there's a k minus 1 in there. I want the number of subsets, not the number of things in the subset other than x. Well, so if I want to make one of these subsets, x is in there, and then I have to pick k minus 1 of these n things. How many ways are there to choose k minus 1 things from n things? And choose k minus 1. So the size of ax is equal to n choose k minus 1. Now, A is definitely the union of ax and a not x. Ax is only subsets that include x, and a not x is only subsets that don't include x. So these are disjoint, right? Like I said, a subset either includes x, in which case it's over here, or it doesn't include x, in which case it's over here. So we can use the sum rule and get that the size of A is the size of AX plus the size of A not x, and we know all those numbers. Those are n choose k plus n choose k minus 1. So the size of A is n choose k plus n choose k minus 1. And indeed, that's what Pascal's identity tells us, that n plus 1 choose k is n choose k plus n choose k minus 1. And if you look over here, this is this famous Pascal's triangle, and Pascal's identity tells us how to get these values, right? 3, for example, and this is the row for 3, has, you get from 3 choose 0, and this is 3 choose 0, and 3 choose, sorry, not 3. This is the row for 2, so this is 2 choose 0, and this is 2 choose 1. So you get it from these two. And so on. All right. So questions about that?
What
Yeah.
does the n represent in this case? What is the
N is just the number of elements.
and k? Why, like, you did k
It's just, this is true for any reasonable k. So this is true for any non-negative integer n and any k between 1 and n. Okay.
You said k is between 1 and n?
Yeah. Okay. So the last thing I want to show you is, looks like a whopper, but it's basically the same thing. The worst thing about it is the name. Vandermonde's identity. And here it is without all the restrictions. Okay, so it says if I want to know how big is, I mean, this is a set of size m plus n, and I choose r elements from it, so that's the number of ways of doing this. And it says that I can build that up from adding up all the different ways of choosing k elements from one of the sets and r minus k elements from the other set. So let's think about whether that makes sense. So let S be a set of n plus m elements, n of which are red and m of which are blue. Here's S. I have a red set N, a red set of size N, and a blue set of size M. This is what S looks like. I just gave two different colors to these things. Does this look familiar? This looks like something just more general than Pascal's identity, right? For Pascal's identity, we had n red things and one blue thing. Now we're looking at what happens when you have more than one blue thing. And again, we'll take A to be the obvious thing. My yellow chalk. Let A be the set of R element subsets of S. All right, so the size of A, we have a set of size n plus m. Each element of A is something we get by choosing R of them. So what's the size of A? Set of size n plus m. We choose R of them. M plus m choose R. Now we need a different way of computing the size of A that's going to give us an answer like this. All right? For each k in 0 up to R, let's let AK be R element subsets of S that have exactly k red elements. Right? Does that make sense? So if I give you a subset of S, maybe like this one, It has some red elements. Could be any number between 0 and R. They could all be red, or none of them could be red. That's where this is coming from. And then the rest of them are blue elements. And let's make that specific. Have exactly k red elements. And that means exactly R minus k blue elements. So, if I want to make one of these sets that has k red elements and has n minus k blue elements, how many ways are there to do that? There's an obvious two-step procedure. First, choose the n elements, or the k elements from this side, the k red elements. There are n red elements, and I need to choose k of them. That's step 1. Step 2 is to choose the r minus k blue elements from this side. There's m blue elements, and I need to choose r minus k of them. That's the size of AK. And now we finish up. Notice that A is actually equal to A0 union A1 union A2 union AR.
What does R represent?
R is the size of the set that we want out of this big set S.
Okay, and K for this situation, what is it?
K is just counts the number of red elements in the set.
Okay.
If it has 0 red elements, then it can't have 1 red element. So these are all disjoint sets. So the size of A is just equal to the sum, K equals 0 to R, of the size of a K, which is, this is the size of a K. That's the end of the proof. So hopefully I've convinced you that this technique of double counting looks really powerful, and sometimes by accident it uncovers all kinds of weird identities that would be really difficult to prove. Like if I just gave you the definition, if I gave you the formula for n choose k, and then said prove this. I mean, if you really struggled at it, of course, it's true, so you can prove it algebraically, figuring out what cancels what all over the place here. But it's a long, complicated mess to do and doesn't really give you any intuition. On the other hand, the proof actually kind of reminds you of what's happening. Yeah, just split the set S into 2 pieces, red and blue, and then whatever you do, there's some number of red things, there's some number of blue things.